In this tutorial, I'm going to discuss unitless analysis. This is useful for a number of reasons. First, it allows us to avoid being concerned about working with specific numbers in our problem. And second, it gives us physical insight into the problem because we can work with a length scale or a time scale that's relevant to the problem. So for our first example, we'll discuss the infinite square well here. This is the potential that defines it in equation 1. We'll just scale the problem to some length parameter a, right? That's the width of the well, so that's what's relevant here. And we'll define this unitless variable u, and so we'll use that. So when we rewrite this, we just get v of u, and those stay the same because if you just divide any length by a, well, 0 and infinity divided by a are still those, but the limits change. So now we've scaled the potential to this length parameter. So for the second example, we have a wave function. It turns out it's a Gaussian centered at the middle of the square well. That's what this offset of a over 2 means. So let's rewrite this in our unitless form. First off, I'm going to rearrange it a little bit, recognizing that this denominator a over 16 squared can be 16 over a squared, a factor by which we multiply the numerator. So I've rewritten it. Now I can make a substitution variables, basically just identify this as u, and now we have this where we use the substitution of variables. In the next example, I'll use the normalization condition, and I'm going to rewrite the eigenfunctions of the infinite square well in this unitless form. Here's the nth eigenfunction for the infinite square well, and I'm using the normalization condition in this equation. And we have u being x over a, so that means du is dx over a. And so I can just then identify dx as a times du, and so we can rewrite this and we cancel the a, so we have this. So now we can see the form of psi n of u, and we don't have to really evaluate anything, so we'll just write this out here. We'll call this equation 2. And you might wonder why I didn't just directly transform psi n of x, but I used the normalization condition. But using the normalization condition allowed us to eliminate the factor of 1 over root a from the coefficient of the sinusoid. And we'll just point out that Fourier's trick still holds. So that works just fine. Next, we'll consider time scaling. So recall that we make the stationary states by taking the eigenfunctions of the Hamiltonian and multiplying them by their time dependence. So here's how we get the eigenfunctions of the Hamiltonian, and here's their time dependence. For the infinite square well, we showed in class that the nth energy is like this, n squared pi squared h bar squared over 2 ma squared. I'm also going to point out that we can say that the nth energy is n squared times the first energy, which is the ground state energy. So we might ask, what's a good time scale for this system? Well, the temporal solutions, if you look up in equation 4, are periodic with period tn, right? Because the exponential is a 2 pi periodic function. So we can solve for the period by setting t to capital T sub n, that period, and then set the argument of the exponential to negative I 2 pi. There's the argument of the exponential, and then we equate it to negative I 2 pi. Of course, with some manipulation, we get this. And then using equation 5, we could write it like this. I'm going to call that equation 6. So I'll just put it here. We know from, well, looking at equation 6, that the higher we make n, the smaller the oscillation period is. So this time dependence oscillates faster. It can go infinitely high or infinitely fast because n can be infinitely large. So in particular, we might want to use T1 because that's the slowest oscillation in the system. So we'll just write that out here. T1 is the longest oscillation period. So it's a good candidate for a time scale. To scale this in time, we'll use a unitless variable, which is equivalent to this. And we'll rearrange phi sub n here, make it more convenient. Using equation 5, we'll write it in terms of E1. And now I'm going to multiply the top and bottom, the numerator and denominator, by 2 pi. And the reason for this is because I'm going to look back at the equation for E1. Actually, we'll use this right here. Right, so that we can recognize that this is 1 over T1. And so I'm going to write this out. So now we have our expression. We'll just write it again. And what's nice about this is we don't really need to specify values for M or A or even H bar. And then we can put everything together and have a wave function or a stationary state that's scaled in time and space. And by the way, that needs a squared there. Okay, we'll call that equation 8. So now we have a unitless version of the stationary state, and that can be helpful in physical analysis.